So, imagine for a second you're watching live TV on your computer. Maybe you're watching Eurovision like 131 other million people. That video you're watching on your computer, and everyone else's computer, all had to come from the same place. And since it's live, everyone's getting the same data at the same time. So, some server somewhere had to generate 131 million copies of the same video to send to all these people, right? I mean, if they were all watching online. And I don't know if you've ever tried to send 131 million packets from a single server, but you end up congesting your network quite a lot trying to send a whole bunch of copies of essentially the same thing. Now, back in the old days of TV, we had a pretty good solution for this. We would stream these channels over the airwaves like magic, and you could tune in to whichever channel you wanted specifically. So the channels were being broadcast out to everyone, and you were choosing which ones to listen to. Now in networking, we have an even better approach to this. It's called Multicast, where we can stream out these channels to only the directions that people need them in. So if you're a network engineer, you've probably heard the term multicast before, but unless you work in a couple of really niche industries, you've probably never actually worked with multicast. So the fundamental idea of multicast is that we can let switches and routers duplicate packets. So if we have 131 million people down here, they're connected up to networks, ISPs, etc. There's a whole hierarchy of devices in here that are splitting off maybe 100 ways at a time. And we end up at the top where our server is. So instead of sending 131 million copies from the server down to each possible destination, instead we send one copy out from the server. The router then the next layer sees I need to send maybe 5 copies out different paths, etc. all the way down the tree until we have 131 million copies at the very end. So today I'm going to take a look at multicast, routed multicast, and using multicast networking to distribute live TV and other video throughout my home network and my home lab. So if you're interested in how multicast works, or you want to stream some live TV around your house, then come along in this adventure. But first, this video is sponsored by boot.dev. If you're a network engineer, you probably know that everything but the most trivial networks relies on automation these days. And one of the best ways to learn how to do automation is to learn Python. With Python, you can integrate all sorts of different vendor APIs, scripts, commands. Basically, whatever you want to do, you can probably figure out how to write a Python script to do it. So if you want to learn Python, try out boot.dev's programming course. So boot.dev is an interactive site that helps teach you programming and other tech topics in a fun, easy to follow way. So all of their lesson content is entirely free if you just want to read it and see what it's like. But for 21 euros a month, if you get a yearly subscription, then you get access to all of their interactive and gamifying features. So rewards for doing lessons on time, getting a streak, things like that. You can also compile all of your code in their platform and check that it's right, which I think is pretty cool. And also they've got a little bear wizard assistant that can help point you in the right direction if you're going wrong. Now use my code APPLEARD or scan the QR code to get 25% off at boot.dev. Now back to the video. So the two most common use cases you'll see for multicast are IPv6 router discovery. In IPv4, this was done over broadcast, and so IPv6 has trimmed that back a bit to make it less chatty and scale better. And multicast DNS. So MDNS is used for different machines to discover each other by name on a network made up of addresses. So I've got my laptop here and a second system that's just a mini PC running Kali Linux, so we can try different communications between them. And let's see what multicast looks like. So here's a packet capture and Wireshark going on. We can see that, there's not a ton of traffic going by. You can see we're only getting a couple packets per second. And most of them are either multicast DNS or ICMP. And actually a bunch of these are related to WebRTC. So if I filter out that guy, then most of them are actually just multicast listener reports. And we occasionally get, so MNDP, and occasionally a little bit of MDNS here. So this is also not that busy of a network. I don't have a ton of stuff hooked up to this network going on. On a busier network, you'll see a lot of MDNS traffic, as every time a network device connects to the network, it'll try querying itself, it'll advertise itself, that sort of stuff. And you'll see big bursts of MDNS as things auto-discover each other. Every time you open the printer menu, it'll query MDNS, etc. So on bigger networks, this can be a legitimate problem, but properly implementing multicast should fix most of that. There we go. So I just queried this and we got a response. So if we look here, it's an Ethernet 2 frame containing an IP version 6 packet, which has a source address that's a link local and a destination address that's a multicast. Inside that is user datagram protocol, port 5353, which is MDNS. And inside that is multicast domain name query. So we're querying pavo.local, type quad A, class internet, and it's a question. And then, so I sent that off to the multicast. And then this guy here sent off a response to the multicast. So his is again an Ethernet 2. And this time it's from a global unicast address, but that doesn't really matter. And it's again a multicast domain name response. So using MDNS, we can discover devices on our network by their .local name. So in this case, I was querying pavo.local. We can also query DNS services by querying pointer records that say like http.tcp or something. Maybe I'll show you what that looks like. So here we've got a number of queries going on, including the DNS service discovery. And then eventually it asks a question of http.tcp.local, and it's asking for pointer records. So anyone who has one of those pointer records can reply. And then in this case, it had one cached that replied itself. But the pointer record basically is pointing to Shelly Color Bulb, .http.tcp.local. And so this can be used to discover services that different devices offer. So if you go and you plug in a printer to your network or connect it to your Wi-Fi, and suddenly it shows up on your list, this is how. Whenever something wants to find the printers, it asks for printer.tcp.local or something like that, or ipp.tcp.local. And then all the printers reply with their own pointer records that have data and stuff like that. So that's DNS service discovery, which also works over MDNS, which is really cool, but not exactly the topic of this video. So while MDNS is really cool and DNS service discovery is really powerful, most of the networks you've worked on probably are not filtering MDNS in any sort of meaningful way. I mean, some admins just block it at the access point directly, but other than that, you're probably not doing IGMP and MLD snooping. And honestly, for MDNS, it's not that beneficial anyway. So if we have a network with, say, 100 devices, we could prune out the MDNS multicast group to only send it down links and Wi-Fi ports where it makes sense, where the devices actually speak MDNS. But out of 100 devices, how many of them are not going to speak MDNS? Pretty much all of them are going to speak MDNS. So we're effectively sending this MDNS everywhere anyway, with just a little bit more control plane overhead to track that. So that's why I've only seen essentially two niches where multicast, like true large-scale routed multicast, really makes sense and is actually used. So one of those is live video. Now video tends to be relatively high bandwidth, especially if you're in the production industry and you're sending around relatively uncompressed live feeds. So then being able to trim segments which don't need specific feeds can really save you a lot of bandwidth on your network. Or you're designing like a multicast live IPTV system, like in my intro example. And in that case, you have so many clients that not replicating at the head end makes a big difference. The other documented, well-documented use case is in high-frequency trading networks. Because if we had to replicate the packet to send to each destination, they would possibly receive it at a different time because it took us nanoseconds to actually send those packets. And that could be unfair. So using multicast there means everyone gets less of a disadvantage and the latency is absolutely minimal. Now I'm not going to pretend like I know how high-frequency trading works, I just know stonks go up. So today for this video, I'm going to be using IPTV as my example. And I'm going to try to stream a couple of different TV sources around my home network using multicast. So remember, Ethernet is a tree. So we have like this, we have some switches, we have some clients, maybe we have some more switches in the middle. It always has to make a tree structure like this because spanning tree enforces that. So we don't know where the multicasts are coming from, but we can know where they're going to. So imagine that some of these listeners here want a multicast and some of them don't. We could then prune any link where that link does not take us to a destination that wants the stream. So now we can remove all the extra links, and only these switches and these ports need to actually participate in sending out the multicast. So then, now that we're making this tree and we're pruning it, we need some sort of protocol to speak that will help the network figure out where these limbs need to be pruned and where they can't be pruned. Some sort of listener discovery protocol, maybe called the Multicast Listener Discovery Protocol, MLD. That's part of ICMPv6 for IPv6. The legacy version was called Internet Group Management Protocol, or IGMP. So you often hear those interchangeably, IGMP and MLD. So let's demonstrate that sort of multicast listener tree pruning effect. So I'm going to play a video on this guy. It's being streamed over my network. I've just got a VM running that's doing the streaming. And I've got my network set up to do IGMP and MLD snooping. So it should trim the tree properly. So over here in Wireshark again, we can see that if I'm filtering for multicast, I'm again not getting that many packets. So clearly I'm not getting video packets here. let's go ahead and play that stream. So I'm just going to play it with FFplay, and I'm just streaming on FFO269. Oh, well, that wasn't supposed to happen. Let's try that again. There we go. Now we got it. This is just the Finnish live TV broadcaster Yle. Switching back to Wireshark now, we can see we've got a whole lot of packets coming in, and they're on this FFO269 multicast group. And we can't tell what they are, but they're, in this case, they're MPEG transport streams. So the neat thing is, I just had to launch the player app on this computer, and suddenly the network knew that I wanted that stream and it should send it to me. The stream was always playing, it's just that the network switch wasn't sending me those packets because I didn't need them. So let's take a little bit of a look at the signaling that makes that work. So that signaling is part of ICMPv6, and it is a multicast listener report. So it's an Ethernet 2 frame, and it's sent to IPv6 multicast. It is an IPv6 address, and it's sent to FFO216. That's the address for these. And it is a multicast listener report. And it says this particular host would like to access these 5 streams. So FFO2FB, and then these 3 solicited no multicast groups, and FFO269, which is my video stream. Also excludes a bit of a weird way of saying it, but it's basically saying that it wants a not source specific. So every so often, everyone that's participating in multicast will send out one of these multicast listener reports that says which multicast groups they want to be a member of. And these get sent out, and they're actually multicast themselves because they're also FFO2. And so every switch that participates in multicast will read this as it comes in and take note of what multicast groups they need to send on that egress switch port. So we got the video stream coming. Click over here and I close the stream. Then eventually I should stop getting the video stream. There we go. Now it stopped. So I didn't send the multicast listener reports often enough, so the switch timed out that port. And this works for anything that's an Ethernet switch. So it could be literally Ethernet switches. But more commonly, it's Wi-Fi access points, actually. And so for them, it's really important not to be sending all this extra traffic over the air and congesting the airwaves with traffic for people that don't need it. So properly implementing multicast like this, if you're actually using multicast, can be a great way to fix multicast network bandwidth problems over Wi-Fi. So since I promised to show you how I'm actually doing this, I'm basically doing this with FFmpeg. So FFmpeg is encoding this MPEG transport stream into a UDP URL. So because IPv6, I put it in brackets. Because it's a link local address, I have to specify what interface I want to send on, in this case ETH0. I've also specified a packet size limit so that we don't have fragments. I'm telling it to use copy, so it's not going to transcode, it's just going to remux. And I told it to copy over all the metadata, so I should have all of the original metadata from my source, which in this case is ULEDL, watching TV1 and outputting to standard out, which gets piped into FFmpeg. So essentially, wherever your video is coming from for your TV distribution plans over multicast, I'm pretty sure you can figure out how to get that into FFmpeg. Now, FFmpeg is like super universal in what formats it can support. It can stream, in this case, there's a Python app that someone wrote to download this. It can input HLS if you have HLS streams. It can import MPEG transport streams, Linux DVB video devices, files, basically anything that digital video exists in. FFmpeg can take that. You can either transcode it into H.264, H.265 if you want, or you can copy it if it's already in a good codec you're happy with. And then from there we can restream as an MPEG transport stream over UDP. So now might be a good time to talk about addresses we use in multicast. Now most of you have probably heard of a MAC address before. Maybe it looks something like this, or maybe if I write it where I have more space. That's a MAC address. There can be multicast MAC addresses too though. So for example, 0108C2000000, that's used by spanning tree protocol. There's no IP address, it's down at the link layer for spanning tree. Similarly, 0108C20000OE is used for link layer discovery protocol, LLDP. But most of the time, when we're dealing with modern applications that aren't down at the link layer, we want to deal with modern addresses, Internet Protocol addresses, IP addresses, if you will. And so, multicast IP addresses exist. In IPv6, they're defined as starting with an FF and then 2 digits that tell us the scope and the type of address. Realistically, the type of addresses you'll see are 0, 1, 3, and 7. So 0 means it's a well-known address. IANA has defined it. That's where you get stuff like Multicast DNS, OSPF, LLMNR, that kind of stuff. You can also put a 1 in there if you came up with it randomly on your own. You can put a 3 in there if it's source specific, which is what I'm using mostly in this video. And you can put a 7 in there if you've embedded a rendezvous point, which is complicated stuff. The next digit defines our scope. So if we have a scope of 2, that means we're limited to a single link. The vast majority of the multicast you've probably seen is link local scope. So this is on the same Ethernet segment, on the same VLAN essentially. Scope 3 is defined as the same topology. So in like hop-by-hop routed networks like meshes, you'll sometimes see FFO3. Thread, for example, uses this. O5 means a single site, so single house, whatever, campus, whatever you call a site. FFO8, that's an organization, so your autonomous system. FFOE is the whole internet, the world. So realistically, you'll probably see 2, 5, and 8 most of the time here. Now, when we actually send this packet, we send it to an Ethernet multicast MAC address. So for example, like FFO2::1234567 that gets sent to a MAC address of 333312345678. Also note that if I have 2 of them with the same suffix, they get the same MAC address. So like FF356612345678, that ends up with MAC address 333312345678. So that of course means it's possible to have a collision in MAC addresses. Now that doesn't matter at the IP layer, but it does mean that every one that shares the same MAC address will get forwarded to the same by layer 2 switches. So if you have switches with IGMP and MLD snooping, if the suffix is the same, the switch will treat it the same. So try to use unique lower 32 bits if you're coming up with your own addresses here. And if you're dealing with legacy IP, you're probably going to see addresses in 224.0.0.0/24, 239.0.0.0/8, and 232.0.0.0/8. So, to test routed multicast, I need, well, a router. So I get this mini PC here. This particular one's made by Protectly. It's got 4 2.5 gig Ethernets on it. So I'm connected with a blue cable up to my LAN in the closet. That's where my multicast sender is. That is on one subnet. In this case, that's subnet 0. Next up, I got this red cable here on a different interface connected to my mini PC. This is a different subnet. In this case, this is subnet 1. So if you're using VLANs on your network, this would be a different VLAN. In my case, it's just a different port because I'm not going through VLAN aware switches, but it would work the same with VLANs. So I need to get this guy to listen to the multicast requests from this, pick up the multicast packets from my LAN, forward them across. So that requires a couple of changes, but let's take a look at how it all works out. So first off, on the sender, I'm still using ULA TV, and I'm using FFmpeg, but I changed this just a little bit here. So instead of streaming to FFO2, I'm now streaming to FF35. So that's source-specific multicast with a scope of this site. So we need a bigger scope now because we're traversing more than just one LAN. So if I used FFO2, that would be link local. It would stop at the first router and it wouldn't progress. We need to progress through the first router. So I need a scope that's bigger than 2. The next common scope is 5, so I'm using 5. I'm also using source-specific multicast now, which means that the receiver has to know the source address, and I'll get to a bit what that means in a bit. But that's an FF3, so FF35. And I also had to put in the hops here, so my hop limit isn't 1, so it can again traverse a router. So I'll go ahead and start up the sender. So over here on the router, which is, I guess, confusingly also running Kali, if I run IP6 mroute, I'll see that I initially have no routes, but as soon as FRR finds this multicast group, it should show up in the mrouting table pretty soon. And there it is. So we have a source address now we resolve to this, and the group address of FF3569. So this is our whole multicast address. It includes both a source and a destination now that we're doing routed multicast. We're also not sure where it's coming in from, but we should figure that out pretty soon, I think. Multicast routing is, of course, backwards from unicast routing. In multicast routing, we route away from the source instead of toward the destination. So as the packets spread out, we don't want to send them back in the direction they came. So we route essentially everywhere but where points back to the source. So a bit on its head backwards, all kinds of wrong compared to what you're used to in routing. And on my listener, I now have to specify a source as well. So I'm looking for FF3569 as my group. And I also have to specify the source address, so let's go ahead and do that. And the stream should come up pretty quickly. And there we go, now I have TV. So this again is routed across this router. So I've traversed across. If I had VLANs, I'd be traversing across VLANs. But I'm routing now. And so I can span this further than just this router and have a whole routed network that's distributing multicast the whole way. And by the way, this is what mroute looks like now. So I have my group address. So the group is a combination of the group address and the source address. And it says it's going input on ETH0 and out on ETH1. So that's what FRR has done. I'm using FRR to do this, by the way. So FRR, free-range routing, it implements most of the major routing protocols like BGP, OSPF, ISIS, and also PIM, or Protocol Independent Multicast. So I'm using PIM, the PIM support, to do this IGMP multicasting. Now PIM is used when we build large routed networks of multicast, but in this case I'm just using it for its MLD support, because it also supports MLD as part of PIM functionality. Now unfortunately, on major router distros, they don't all support PIM. So OpenSense, for example, includes FRR and uses FRR for BGP and OSPF and things like that. But they haven't compiled in support for multicast for PIM. So they would have to compile it in for us to be able to write a custom config on the back end. It's kind of a niche application, so I see why they don't do it, but it would be nice to have it compiled in. I'm just running on vanilla Debian Linux here. You should be able to install FRR and OpenWRT, although OpenWRT makes you install every single daemon separately. So you'll need like Zebra, Core FRR, what's the other one? Static D and PIM6D to do MLD, or PIMD if you're doing legacy IP. And my config's pretty simple, so I just got interface ETH1, IPv6 PIM, MLD, version 2, etc., etc., etc. You can also do some filtering, and if you want to only allow certain groups through the router or stuff like that, just go ahead and check out the blog post, link down below for that, for all the commands examples. I have FFmpeg examples too if you want those. And just like before, I can stop streaming here, and now the router should stop forwarding to this subnet at all. And back on the router, I now have removed ETH1 from the output interfaces, so it's not sending, it knows this multicast group exists, and it's going to keep tracking it, but it's not sending it anywhere, so it's inputting it on ETH0, but it's not going out ETH1. So even if your switches don't support MLD or IGMP snooping, the router still does. And so the router is still pruning these streams to interfaces it doesn't need to, like separate VLANs. So now that I get routed multicast working with one router, I guess the next step would be more than one router. I'm not going to go that far in this video because I think a large majority of networks are one router networks, at least by count of networks. And going further than that means using PIM, Protocol Independent Multicast. Now it's actually its own protocol, it's not exactly independent, but it's independent in the sense that it relies on the unicast routing table to make multicast routing decisions. So that would mean you need to have a full routing table, either based on like OSPF or BGP or both, and then you layer multicast on top of that, routing away from the source instead of toward the destination. So it uses the unicast routing table to point backwards toward the source. Now that's honestly not that much harder to set up once you have routed multicast working, but again, this video can only be so long. So as for where I'm going to go with this in the future, you might remember my GPON video, maybe link up here for that, where I built a whole passive optical network. My goal is to extend that to bring multicast IPTV across the PON, and then I'm going to try to set up like an OpenWRT based CPE router that'll do multicast to unicast, so I can do multicast on the PON, unicast like web-based all of my customers, and try to set up like a mock ISP IPTV system, like one of the major providers in Europe would do. Now if you're interested in doing this at home, there's quite a lot of sources that can feed into FFmpeg. So I've linked in the description a whole blog post that has some examples of how to run FFmpeg, if you're not familiar with it. Some of the commands I used. I've also included my FRR config for routed multicast, that sort of stuff. And I've got links to a couple of other videos that I found useful here. In particular, Tall Paul Tech down in Australia, he's been using Raspberry Pis to capture digital TV over the air. So he was originally doing DVB-T. I'm guessing Australia has moved the DVB-T2 now, so he probably has new capture cards, but he's using software-defined radio to decode essentially every single over-the-air TV channel he can get, sending that all over multicast, and then he can watch potentially all of them at once, but realistically he's picking a specific one he wants to watch at a given time. And you can do that same thing for multicast audio if you want to do DAB, DVB-T, DVB-C cable. I've seen someone do it with DVB satellite, those sorts of things. In my example, I use an HLS stream from Yle TV, so that's the national broadcaster in Finland. Also, by the way, I got one more thing. So for my one last thing, I have this thing here. Guess I should reach over and turn it on and lift the lid. One side of it's a little bit broken over there. And yeah, let's go. There it goes. It's kind of quiet. So, sorry it's hard to film. I'm actually recording this segment at 50 FPS instead of 60 because this is a 50 Hertz PAL TV. And even then, it looks kind of awful. But, yeah. So this is a very beautiful TV from 1989. I like to get running to put in my kitchen. And I was hoping to set up some sort of relay to broadcast analog PAL TV channels to this from the multicast distribution in my house. Okay, back to 60 FPS. Anyway, if you want to help me with this project, I could definitely use some advice on analog RF signal wizardry. I do have the equipment to do like RF over fiber, but not to generate the analog signals. So Discord, link down below, would be a great place to help me with this project and see if I can get it off the ground. Also, thanks to boot.dev for sponsoring this video. Use my code AppleArt or the QR code to get 25% off. And I guess I'll see you guys on the next adventure.